Okay, so this is then the code for this very simple model for just a single country. We just get the data for this country, the time points. This is just going to be from 1 to 30 or whatever, how many time points we have. And we're going to align everything from the day where the country crossed 100 cases. So that just removes a lot of the early days where there are just a few cases and there's a lot of noise in the data. And here we're going to get the confirmed data. And then with PyMC 3, every model starts with this code. We just instantiate the model class and bind it to this model object. And this is purely for bookkeeping. So all this does is it says everything that happens indented under here is going to be tied to this model object. So nothing crazy going on. Robert, am I still on?
Yeah, you're doing great.
Cool. So then the first thing we do is we define our parameters of our model. And as we just saw, we have two parameters in our model, the intercept and the slope. And we're not just defining them, as I said before, we are also setting priors. So without having seen any data, what do I think about likely values for the intercept parameter? Well, because I started them from 100 days on, I set it to 0 where the country crossed 100 cases and know that it's going to be in the vicinity of 100. Right? So that is just the way I set up the data. So I can inform the model that it's going to be close to that vicinity and then set a standard deviation for that as well, which is fairly wide because it probably will be more than 100 days. And then the second parameter is the slope. And again, I'm just placing a prior distribution on that. Oh, and so the first argument is always the name and then the parameters of that distribution. And so here I'm going to choose a normal distribution as well. Just that is pretty natural choice, but of course you can do different choices. And here, this is going to be the growth rate of the spread of COVID-19. And as I said before, also we have some information on that. So it is supposed to be roughly around 0.3. So that is what we're going to use here. The model is going to refine that value and find the best fitting value for this particular case that we're looking at. It might be different, but it's a good starting point again. And we're going to say, okay, we are fairly confident that it's going to be around that value somewhere. And then once I have defined my two parameters, I just follow through the math and say, okay, this is now the exponential. That's just the formula that I had before. I define an error term, which is here half normal. And then once I have defined my parameters, I just need to tie them together with the data. And the way I'm doing that in PyMC 3 is I define, or in general Bayesian statistics, you define a likelihood function. And here I'm using a log normal distribution. And that choice is definitely contestable. Here we are dealing with counts, and usually for counts you would use a Poisson distribution, which is the correct distribution to use, or a negative binomial. I started out doing that, but it gave me a lot of problems. So that's really the main reason why I chose the log normal here. It seems to work way better, but that is something that I need to drill in deeper. So I still think the Poisson would be the more principled one, but yeah, so that's just a limitation of the current state of the model. It takes the growth rate, but here we have to supply the log domain because we're using a log normal distribution. The benefit, of course, of the log norm is that it's positive, so at least we have that going for it. And so the standard deviation is so this is the mean, and then we have our sigma, which is the error term, and then we have our observed. So this is what turns this into a likelihood function. We supply our actual number of cases, which is the data, as the observed keyword argument. So that concludes the model specification. And then when I execute just this part, nothing really happens because I just specify the model. Next, what I want to do is I want to actually run inference. So I just call the sample function, and then I get back what is called a trace. And that is the sample from my posterior distribution, or what I believe about the parameter values after having seen the data. And then I can also sample from what is called this posterior predictive, which is what the model thinks the data looks like. and this will become clear when we actually look at it. So here we can now look at the so-called posteriors, which again is the belief of my parameters after having seen the data. And if you were to not do this in the Bayesian framework, these would just be single digit scalar values, right? So you get a, say 115, right, is the best fitting value. But again, because we're in the Bayesian framework, we have uncertainty here, and that is expressed in the width of that distribution. So we think that the intercept is 115, but it could also be 120, could also be 110. And we think that the growth rate most likely is going to be around 0.34, maybe 0.340 something. But it could also be way higher, could also be a little bit lower. But you can see it's in a very narrow range, so we actually have a lot of certainty that the growth rate is going to be in this particular value, just because the data is fairly informative, and also because we set our prior here. And then this is just the error term that we're looking at. There are two lines because I ran two chains, so this is just to check for that the sampler did actually the right thing. So we want to know that both sample chains that I ran arrived at the same distribution. So we can see that that has happened here. So it puts more confidence that the sampling actually worked correctly.
This is Robert. Just one quick question. What country is this data for?
Yeah, so this is the US. Yeah, so that's just the one that I chose here. But we will look at what others look like too. So, and now we can look at the predictions of the model. So what does the model think when we simulate data from the model after we have fitted? We can look at how good it actually describes our data. So in red, you can see the confirmed cases over time, since we crossed 100 cases in the US. And in gray, you see what the model predicts the rate at each particular time point to be. And a couple of things to note here. One is, well, the exponential actually does provide a pretty good fit here, right? So overall, it seems to explain the data. Maybe here we are on the lower end of this, so maybe this is where the exponential starts to break down, but so far it still looks pretty accurate. And the other thing which we can also see is that we don't just get a single prediction, right? Because if we're in Bayesian framework, we're always dealing with probabilistic distributions, and that carries through all the way to our predictions. So we don't ever just make a single prediction. We're always going to predict a whole distribution. And that is also then reflected here. So these are actually many, many individual lines that I'm drawing here that make up this gray band. And so you can see as more time progresses, we have more uncertainty around this, and we will see when we project out further and predict the future. So currently we're just doing post-prediction anyway, right? We're just predicting the past, but it's still really good for model validation. So if the model were terrible, it would not describe the data well. So here we see that it does. So this is a good semi to check.
Quick question. One question I have here. What is the ESP parameter? Or could you explain that a little bit more?
Sure, yeah. So EPS is just epsilon. So that's just the error term of the normal distribution. So okay. When you, for example, you run a linear regression, right? You assume that your data comes from a normal distribution, and that, and then you have an error term. So it's always y equals mx plus b plus epsilon. So that's just.
And you use a half normal here to make sure that it is strictly positive.
That's exactly right. Yep. Thanks for highlighting that. So there's all kinds of different choices you can make. But yeah, we do know that, of course, the variance can only be positive, or the standard deviation. And that's why we're choosing half normal distribution, which is a normal distribution but the negative section is cut off. So we're not allowing negative values because, yeah, it doesn't make sense. And when I'm talking about priors, this is also sometimes a critique on Bayesian statistics, that these priors are basically allow you to do everything, or they should be objective. But really, I think, well, one thing is these priors are very explicit. So like everyone can now see exactly what type of assumptions I'm building into my model. And you might very well disagree with this, right? You might say, well, actually, I think this is the wrong value. Well, then you can take the model, and change it and see what kind of different assumptions and predictions the model generates under new information as it becomes available. So, and in general, it's impossible to do any modeling without assumptions. So here the assumptions are explicit, while with other approaches, like for example, frequentist statistics, they're often hidden. So just because I get that question a lot.
One question I get here is, could you explain the country variable and the likelihood? The person's asking where does country variable?
Right. So actually, yeah, this is unnecessarily complex. So really, this is also just the name. So country is just the string US, and it just named it, or often it's called for observed. Yeah. So yeah, it's just the name, and then here I'm just passing in the parameters.
So and every time you are calling one of these distribution, you're instantiating one of these distribution, the first argument is the name of the variable.
Yeah, that's right. So this is purely for bookkeeping, and so you can see like it's always repeated here. So I call this B, but then I also have to give it the name B, which is a bit annoying, but there's purely technical reasons why this is necessary. But yeah, so it's just specification. So the first parameter is always the name, if it's a likelihood or a prior. So yeah, and it doesn't matter what you call it.
I have a question here. Maybe you want to hold this to the end, but it's about, I guess, just sampling bias in the data. So the question is it not true that the number of confirmed cases should be the minimum, since because the undetected number of cases is greater than 0? Yes. So in other words, you're not accounting for undersampling in the data in this model.
Yeah, that's a great point and completely correct. That is definitely a limitation of this model. So here we're really just modeling, the confirmed cases, which is going to be lower than the total number of cases, which we don't know. So, but certainly we could use this model to try and estimate that. So it's not what this particular model is trying to do, but you can certainly imagine that this is what you can build a model to try and do, and that would be quite useful, right? And yeah, I can talk about this later also with another model where this makes a little bit more sense, but that's a good point. Like using these types of models to infer this, and then you would set this as the limit, the minimum number of the data is the minimum number of cases that you know you'll have at least.